Good afternoon, everyone. This is the third and last lecture in the series about fatigue failure theory, and it deals with the general case term fluctuating stress, which means that you have some mean stress. Mean stress is not zero, as in the fully reversed case, and the minimum stress may not be zero either, which is the repeated case. So we have some minimum, some maximum, and some mean value of stress to deal with. So this puts us in the right-hand column of my category over here, my category matrix. Category 2 if it's uniaxial stresses, Category 4 if it's multi-axial stresses, which would mean you have some sigma x's and some sigma y's, and maybe some tau xy's, and maybe even some sigma z's if it's three-dimensional. The three-dimensional stress cases are relatively rare, but 2D is very, very common. And in the last section of Chapter 6, I deal with this case of multi-axial stresses in fatigue, and it's a very complicated topic and one that isn't yet fully understood. There's still research being done on it. I'm not going to lecture on that, but I would suggest that it would be a good idea to take a look at that last section as well. So I'm going to talk tonight today about Category 2 primarily, though we'll get into Category 4 a little bit. So when I have something other than fully reversed stress in a fatigue situation, then I will have a value of mean stress, a non-zero mean stress. And there's lots of test data that show that the combination of both alternating and mean stress is more dangerous and debilitating to the material than just the fully reversed stress itself. And that's bad enough, because we've already discovered that your allowable strength, the usable strength of a material, is of the order of a fourth to a third of its advertised value statically, the ultimate tensile strength rather. And when we get through with all the factors and whatnot for endurance strength, we find we're down around 25 to 30% of the number we started with. That case is on the vertical axis here. This is the alternating stress axis, and this is the mean stress axis. Now this looks a little bit like an SN diagram, but it's not. It's totally different. The SN diagram is actually in this plane and it's coming out at you. And I'll show you a 3D representation of this in a minute that shows all three planes. So if I have no mean stress whatsoever, then I'm operating on this axis, and this value shown here as 1 because everything's been normalized is the endurance strength or the fatigue strength of the material, which is that number that we would get by first taking the ultimate tensile and cutting it in half, and then adding the load factor and the surface factor and all that stuff till we get down to something around 30%. So that's what that value is on that axis. But now as we introduce mean stress in addition to that, and it's tensile, we find that our parts fail at values below that so-called endurance limit. And these little letters here all represent test data, and those are the points at which the various pieces failed. And they had to be tested for millions of cycles in order to get that data. The top plot is for steel, the bottom plot's for aluminum, and they look very, very similar. The lines that you see drawn on them have names. The parabola is called the Gerber parabola, like the baby food. And the straight line is called the Goodman line, and both of those are researchers who came up with the concept to look at the data in that respect. You can see that the Gerber line pretty well goes through the middle of the scatter and is considered to be a good fit to the data, even though the R squared value is not going to be very large because you've got a lot of scatter in the data. But if you did a parabola fit to the data of all those tests, it would look like that Gerber line. That's considered to be the most accurate representation of the statistical parameter of this mean stress versus alternating stress. But notice that there's an awful lot of parts breaking below that parabola. And we want to take a line of that sort as a limit to determine our safety factors. So it's generally believed or felt by engineers that the Gerber line is the best to use when you're trying to analyze forensically a fractured part, because it's going to give you accurate data. But it's not a very good line to use for design on the front end. So most engineers will use the Goodman line instead. And I'll show you these lines again along with a third one in an upcoming slide. Now, we've talked before about the effect, the positive effect of compressive residual stress on the fatigue case, because it tends to close the cracks. It lowers the threshold. We have to then get the tensile up above that threshold before it really is seen by the part, and all that good stuff. This now shows test data, and these are actual test failure points for aluminum and steel both. There's supposed to be a difference in appearance there, but I don't see it. Aluminum, they both are circles. I think one is supposed to be a fatter line, but it doesn't show up very well on this plot. So some of these are aluminum, some of them are steel, all mixed in together. But this now goes into the compression regime. So here we have tension to the right, compression to the left, shown as negative values. And this is also the same mean stress versus alternating stress, or vice versa, alternating on the vertical axis, mean on the horizontal. But the data are taken back into the compressive regime, and notice that the stuff is stronger under compression type stress, and it breaks at values, it has more strength, put it that way, than the endurance strength and tension, which is right here on this axis. This is the alternating axis right here. So that again indicates the compressive stress is your friend, and tensile stress is the enemy over here. So you could continue that Goodman line back into the compressive regime, because you might have mean compressive stress, and you might even have some alternating compressive stress in a given situation. But because engineers are inherently conservative, we don't take advantage of that, and we're going to run the line across at the endurance limit. That'll come up in another slide in a moment, too. So this shows the Gerber parabola that we just saw sitting on a bunch of test data. The Goodman line, which is pretty much underneath most of those breakpoints. There were a few that were below the Goodman line. In the aluminum, there were quite a few, in fact, which is, again, why we have to use safety factors. And it shows another line here labeled the Soderberg line. And if I'm not mistaken, Mr. Soderberg is one of the earlier contributors here. I think it was Soderberg, Goodman, Gerber, perhaps, in that order. And this is a long time ago. This data has been around a while. Mr. Soderberg must have been extremely conservative, because note that the Goodman line simply connects the fatigue strength or the endurance strength, and whether it's endurance strength or fatigue strength is dictated by the type of material. We don't talk about an endurance strength for aluminum, because it never levels out. So we talk about its fatigue strength, and I use the term F, the subscript F for that. And if you're talking about a lifetime less than 1 million cycles, in other words, if you're only requiring the thing to last 100,000 cycles, that's its lifetime, then you could back up the curve, the SN diagram, and get a larger value for endurance, or rather for fatigue strength, larger than the endurance strength, because they don't care about going to 1 million cycles. So that's the difference between the E and the F. And that line connects, the Goodman line I'm talking about, connects to the ultimate tensile stress, or strength I should say, on the mean stress axis. That, of course, is where the part will break with a static load, right? Notice I also show the yield line here. That's going up to the value of SY on the other axis off the paper. And it's possible that I could be within the Goodman line but outside the yield line. If I had a very large mean stress, I might just yield it on the first stroke, on the first cycle, right? So I need to have that yield line in there. As I said, Soderberg was very conservative, and he said, I'm going to avoid that problem by just ending my line at the yield strength of the material. And that Soderberg line is pretty much under the scatter completely, with some room to spare. So if you're very conservative, you can use the Soderberg. If you're moderate, use the Goodman. if you're in a mood to be a gambler, the Gerber, because a lot of the failures are below that line. That's a bit of a gamble there. I think most designers, as I said, will use the Goodman line. I don't see the Soderbergh used very much. When I was a student, which is literally 40 plus years ago, they were pushing the Soderbergh back then, but there weren't as many data available that long ago on this phenomenon. So I think nowadays the Goodman line is sort of it. But you can use any one of them, and you'll find different books will stress different ones. We can write equations for these lines very easily. I mean, you know how a parabola is just a squared term equation. And this is in terms of alternating strength, S sub A, just a generic term for alternating strength. That's a sit-in for either S sub F or S sub E. It's just a generalized alternating strength. Endurance limit times 1 minus sigma m squared. Now sigma would be your applied stress level in the mean direction, divided by sigma ut squared. That's the ultimate tensile strength. And that fits the experimental data very well. Goodman line, it's a linear line, so it's the first power, similar expression, 1 minus sigma m over sigma ut. And the Soderbergh line puts sigma y in instead of sigma ut. So we can use any one of those three as our reference. Before I leave that slide, if my combination of alternating stress and mean stress is within these envelopes, whichever one you want to pick, then you say that's safe. Because when you reach the line, that's defined as failure for the Soderbergh theory, the Goodman theory, or the Gerber theory. So on or outside the line is failure. So you want to try to keep your stresses inside by some comfort factor, which is our safety factor. So this is an attempt to plot the three axes that we've so far discussed. This axis is number of cycles, and I've gone from 10 to the 0 to 10 to the 8 here. And this is the alternating stress axis. So this picture, if I look in, there's my eyeball looking in that direction, and draw that side view, each of these lines is an SN diagram, strength versus number of cycles, showing an endurance limit, so it's presumably steel. And what I'm doing is I'm cutting through this at different levels along the mean stress axis. So the mean stress axis is going back, taking my endurance strength down to 0 at SUT. So looking in this way, I'm looking at the alternating mean plot on which I can draw the Goodman lines. So these are all Goodman lines. I'm sorry, I'm calling them constant life diagrams here. But in fact, it is the Goodman line as well, because I have alternating stress on this axis and mean stress on this axis. See sigma A, sigma M. So they're also called constant life diagrams because each of those is taken at a different level of n. Okay, so one of those is at 10 to the 8th, and that's 10 to the 6th, I guess, 10 to the 4th, 10 to the 2, and 10 to the 0. So obviously, as I have fewer cycles, my fatigue strength is better and better and better, and if I have one cycle, it's the SUT. That's not a fatigue case at all. That's just static loading. So you can plot that three-dimensionally as a surface. So again, if we are dealing with fully reversed stress, we only need this picture over here. But if we're dealing with fluctuating stress, we need this picture as well. We have to find out where this intercept is by the same techniques we've discussed. Start with the SUT, cut it in half, apply the factors that are appropriate, get a number. That's my point on this axis. Just runs down to SUT on the other end. So this is what I use and what I propose to you as a good solution. I've extended the line so you can see the SY just ends up at SY up on this axis. That's my breakout point for static loading in essence. The data shows that it continues more or less at the same slope back into the compressive regime, but we, being conservative, say we'll just level that off. And we could have yielding on the compressive direction as well. So that puts a limit there. And here's our Goodman line going off to SUT from the endurance of fatigue strength. So the gray area is our safe zone. And again, we're going to have to calculate a value for sigma A and sigma M separately. Same equations, but you'll have different forces, right? Because you may have a different value for alternating the mean in a given case. And find out where we are in this gray area here. And then we will determine a safety factor based on the relationship to that line. Now we have to deal with stress concentration again, and it becomes a little more complicated when we add in the mean stress. And let me hark back to something that I said a couple of times when we started talking about static stresses, and it becomes applicable here as well. It's generally believed that if you have only static loading and ductile materials, that you can pretty much ignore stress concentrations because they self-correct. Locally in the notch, the material will yield. And when it yields, the stress comes down to the yield stress. And it can't go above it anymore because the material has moved. It has taken a set locally. So it's somewhat self-healing. And if I only put that static load on once, and the first time I put the load on, the thing goes, oh my God, that hurts in my back, and it yields, and it no longer hurts. And so if I do nothing else except leave that load on, I should be okay. But if I start to cycle that load, that's a whole new can of worms. And now I'm going to have to worry about that stress concentration, even though the material is ductile. So now in this new situation with fluctuating stress, we have both mean loads and alternating loads. So if you want to be really conservative, you could say, well, I'll calculate the stress concentration factor like we did in the last round of discussion. We take the K sub T out of one of Peterson's tables, like you did on the quiz yesterday, and you factor that typically down based on the notch sensitivity of the material. So if the material isn't very sensitive to notch, then I can reduce that number a little bit. And I call that K sub F, fatigue stress concentration factor. If I were to be very conservative, I could simply apply that K sub F to both the mean and the alternating stress all the time. And I would be safe because, as I just said, on the mean stress side, the thing can somewhat self-correct. But it may not always self-correct. So that leads to this presentation that I'm going to go through right now. So here we show a generalized fluctuating stress case. It's going to a negative value, compressive, and then to a positive, a tensile value. The mean stress is someplace in there. So I have an alternating component, and I have a mean component, and I have a delta sigma called the range from the top to the bottom, the max minus the min. And if I have a stress concentration in the part, this is a simple situation with just axial load on this rectangular piece with a hole in it, then we would expect to get, if we exceeded the yield strength locally in here because of the stress concentration, we would develop little plastic zones in here, which is the material yielding and sort of readjusting to the load. This curve over here is what material people do this all the time. They say, let's assume an elastic, perfectly plastic material, which makes the stress-strain curve really simple. So here's the elastic region of the stress-strain. There's the yield point, and then you assume that it just stays at that level until it breaks. We know that it keeps going up and has some shape and all that jazz, but this is a much simpler way to handle it mathematically. And it's conservative because really it goes up like that and then it breaks, right? So it's considered okay to do this by the materials folks. So if we assume that once we reach this yield point, it just gives, and no matter what more strain you put into it, it's never going to get above that yield point. Then I have three possible cases that could occur. And they all depend on how big is the overall range from top to bottom, max to min. If I exceed the yield strength, S sub y, with my sigma max, then I'll do some yielding. That's shown in the center bar here, center picture. So I run up the elastic curve and I exceed the yield strength of the material, and it moves over in strain. And when I relax the load, it comes back down a new line parallel to the elastic region, and I now have a permanent set. The set now you recognize is local. It's just in here. So the hole maybe got a little egg-shaped. It didn't affect the overall shape of the part, so I don't even notice it. But it yielded. If I had very large negative stresses as well, in other words, if my compressive component here went beyond the compressive yield strength, I could yield on both sides, and then I'd have a band like this, and I'd go around this all day long. If my maximum stress is not sufficient to pass the yield point, then I just run up and down on the elastic piece all day long. Right? So no yielding occurs. Well, if no yielding occurs, then there's no self-healing, no relief, and the crack can continue to grow. So that's the most dangerous case. So if we're going to simply calculate based on the largest load, the largest moment, the largest force, or whatever we might have, what's the stress under the maximum load? And does that exceed the yield point? If it doesn't, then we say, that's not a good situation because I'm not doing any kind of localized yielding to smooth things out and so forth. I'd better use the entire K sub F factor on the mean component as well. That's the conservative approach. On the other hand, if I do yield, then I could afford to knock down the K sub F a little bit to account for the fact that there's some correction going on in the material. And if I'm actually yielding both ends here, I could then probably just forget it and call it 0. Because now, if I make the K factor for the mean stress 0, then the mean component goes to 0 because I multiply it by the stress, right? And that, in effect, is a fully reversed case. So if I am exceeding the yield point on the upstroke and the backstroke, tension and compression, my mean stress is 0, isn't it? So then I'm back to a fully reversed case. So we're going to have 3 possible values for what's called KFM, K fatigue mean. And it'll either be full value of the KF, whatever that turned out to be, or it'll be somewhere between 1 and that value, or it'll be 0. And if I plot these 3 regimes, this axis is the maximum value of stress. And right here, this dotted line represents the value of SY divided by KF. We're going to apply the KF to the calculation because we have the stress. We know we have a stress concentration, and I want to know, does that stress in the stress concentration yield the part locally? So I'm going to multiply the maximum stress by the K sub F and compare that to the yield strength. Did I yield at the end of the crack is the question. If I don't, then I'm going to use the full KF for KFM because I never yielded. But if I start to yield it, then I'm going to work this down until when I get to twice SY, which means that I'm exceeding it at both ends, I now in effect have a fully reversed case, and I'll knock it down to 0. So while I'm in this regime here, Dowling, I think, came up with this equation. I'm not sure if it's original with him, but I first encountered it in his work, so I'll give him credit. We take the yield strength and we look at the alternating stress and the absolute value of the mean stress, multiply that by K sub F, and that will become our K sub FM. I'm going to go through an example with you on this that hopefully will clear some of this up. This is starting to get complicated, I realize. All these different things going on. We have, is it fully reversed, or is there a mean value? We got to figure out the endurance strength with all those funny factors for load and surface and all that stuff and get the right value for fatigue strength. And now we're introducing this possibility of mean stress as well. So this is just a summation of what I said. So if Kf times the maximum nominal stress is less than Sy, I use the entire amount of K sub f for Kfm. If it's greater than Sy, then I have yielded locally in the notch, and I use this funny formula. And if it's greater than 2 times Sy, then I say I've clipped it on top and bottom, and my mean stress is effectively gone. So now the question is, how do we figure out a safety factor? I hope you understand that we have this envelope, right? From your side, alternating stress here, mean stress here, Goodman line coming down, yield line over in the corner. Goodman line is primary one, and we're at some point in there. Some sigma A, some sigma M. We're sitting someplace in the gray zone, so we're safe. How safe are we is the question. Well, it turns out there are 4 possibilities. I call them case 1 through 4. And which one you have depends upon predicting the future. Today I have a certain load scheme on this device. And I have, let's say, an alternating stress of, well, let's talk in terms of load. I have an alternating load of 500 pounds. And it's sitting on a mean load of 300 pounds. So it's going to go from, starting at the mean, from 300 up to 800, and then back down to minus 200, and then up to 800 again, minus 200, 800 all day long. Okay? If that never changes over time, no one comes along and throws more dirt in the truck, or drives faster than I thought they were going to drive, or whatever. If nothing changes, then I'm fine. I just calculate the safety factor as if that ratio stayed the same forever. In other words, the 500 over the 300 is going to be never any different. That's case 3, as it turns out. But there's another possibility that maybe the alternating never changes, but somebody jacks up the mean load. So they put too much dirt in the truck. But the truck goes over the same size bumps, so the spring sees the same sort of oscillating load, but the mean load is a lot bigger because they got more dirt in the truck. So that would be a case where the mean stress increases and the alternating stress does not. And that's the first case I show here. So here's a Goodman line and a yield line over here. And I have some stress state, sigma A prime. These are expressed now in von Mises, note the primes. So that accounts for the combined stresses, or I got some torsion thrown in with the bending and all that jazz. I convert it to a von Mises. So this is all tensile stress in this picture. And I'm at some point Z. Well, if I keep jacking up the mean stress and I don't change the alternating stress, then I'm going to go along this dotted line. And if I get to point Q, I break. Now, recognize that if I started out higher up here with a larger mean, I might break out of the Goodman line. So I've got to check both of those. So this is what I call case 1. Case 2 is the reverse of that. It says, okay, when the mean stress is never going to change, we think, under circumstances of whatever sort this thing will see in its lifetime, but the alternating stress might go up. Well, if that be the case, then I'm going to go out along this vertical dotted line, and I'm going to break out at P. So notice that my safety factor will always be a ratio between the distance it takes to break out of the envelope over the distance where I am now. Right? So that's like better than 2 to 1 in that picture, probably 2.5 to 1 or something like that, because I'm less than half of the way out the door. Okay? These case 1s and case 2s I don't think are very common. Not in my experience anyway. Doesn't mean they don't exist. This is the one that in my world, where I'm dealing with machinery that sits on a factory floor and runs at a certain speed all day long, is the most common in my world. Because they may come along and jack up the speed, but that will tend to lift both of them up by the same amount. And so now I'm going to go out on a dotted line that's just an extension of the line that gets me from the corner to my point. And so now my safety factor is RO divided by ZO. And we can write expressions for those, so we know the equations of the lines and so forth, right? So it's just the intersection. R is at the intersection of this line called the load line and this line called the Goodman line. If I write the equations for those two lines, solve them simultaneously, I get the intersection, and that's my equation, which we'll see in a second. And what I call case 4 is the general case in which I say, I have no idea what's going to happen in the future with these loads. You know, the alternating may increase and the mean may increase also, but not in the same ratio. I have no data, no way to know what someone's going to do to this assembly when it's out there in the world. And I think this is probably most realistic with any kind of vehicle, because you don't know what they're going to do with the vehicle. So here I want to find what's the shortest way out. Well, the shortest way out of the envelope can be found by taking your compass, setting it there, and increasing the radius and drawing arcs until you find an arc that's tangent to the envelope, right? And that's the shortest distance out to the envelope. And I show that as point labeled S. And for a graphical solution, I could bring that arc from my compass down here until it intersects this line extended, which I've labeled S prime. And I could then measure, if I've drawn this to scale, the distance S prime to O and divide by the distance Z to O, and that would be my safety factor. So this will typically be the most conservative of the bunch. So that doesn't necessarily hold true. If I have a very large alternating and I'm going to go up further on the alternating, I might break out with this faster than I go out this way. So what I typically do is calculate all 4. And unless I have some good knowledge about the history of this kind of device and how it's going to be used, and I say, well, it's going to be a case 3, I might not bother. But it doesn't cost me a lot to calculate all 4. It's just 4 different equations, and I build them into the spreadsheet, push the button, get all 4, and I pick the smallest one. That's my worst case, if I have no idea what's going to happen in the future. So I didn't show you the formulas here, but they're in the book. And as I said, they just come up. This was a little more complicated because I got to figure out, what that radius is out to the line and so forth. It's just geometry. So they were derived using plane geometry. And we'll see them in the example that I'm going to go through now. So this is the example 6.5, which is a building upon 6.4. And I walked you through 6.4 the other day, where 6.4 dealt with fully reversed stress on this same part. So now I've changed the loading conditions for the part to a fluctuating stress. And so I have a maximum of 1,100 pounds, minimum of 100, and mean of 600. I think it's pounds. Could be newtons. And we looked at this beam the other day. I explained why I did this rather than just clamp a straight piece in the wall, because that gives me a stress concentration factor of 2.0. And I can get lower than that by putting a generous radius in there, which is what I did that for. I got it down to 1.2 or something like that. Ranges from 1.1 to 1.5 for that case, according to Peterson. So I'm going to start this analysis with the design I ended up with, same dimensions for the fully reversed. And if you recall that, I picked some numbers out of a hat to start out. I think it was an inch wide and maybe it was an inch deep and inch and a half wide or something like that. And it turned out to have a safety factor less than 1. So I jacked the dimensions up a little bit, and I got it up to 2 point something or other. Or 2.2 or something like that. Okay, so I'll start with those numbers, which are here someplace. I'm going to assume that I will use a medium carbon steel because it's nice and ductile. It's got an endurance limit, has a knee, and it's pretty low notch sensitivity, so that's a good choice for this particular case. If I don't need the hardness for wear, then I typically will not go up into the high hardness regime because I'm going to lose ductility. I'm going to pick up a lot of strength. I mean, the ultimate tensile strength goes way up, but I lose ductility and I pick up notch sensitivity. So I sort of chase my tail a little bit in the fatigue department by going to higher strength steels. Where I have to do that is where I have rubbing contact or rolling contact between materials. Ball bearings, a good example. Those are made as hard as you can make the steel, because otherwise they're going to wear out in a hurry. And luckily, a lot of the loads, the stresses in those are compressive, so it's not such a big deal. But there's plenty of other applications. Any machinery where things are rubbing on one another, cams, gears, those are usually made hard if they have high loads. But this one is just a bracket of some sort. It's holding up some kind of a roll, I said here somewhere. So here's the numbers that we ended up with before. 2 inches wide, 1 inch deep. Big D, which is the piece in the wall, is a 1 1/8 inch. Half-inch radius in the notch. Distance A is 5 inches and distance L is 6 inches. So that's where we ended up with the fully reversed case before. So I start off by finding out what my components are for the mean and the alternating. So in essence, what I'm going to end up doing with this case, a fluctuating case, is I'm going to have two almost identical stress analysis computations. Equations are typically going to be the same because the loads, the cross sections are the same in both cases, and the loads are in the same direction in both cases. I just have a different value. So I've got a value of, 600 for the mean and 500 for the alternating. So I set the same set of equations up for both, just change the numbers. So I'm doing it in a spreadsheet or MathCAD, MATLAB, TK Solver, whatever. It's very simple to do. So we find the reaction forces and so forth. We've got to find the moments. So we use a standard beam analysis to get the moments, and we find we get 2,500 pound-inches of moment alternating. The moment's going to look the same, right? So the force does this. The moment's going to do that too. It's just a force times the length. The mean moment is 3,000 pound-inches, and we're going to need the maximum moment because we want to get a maximum stress, and that's 5,500 pound-inches. We calculate the cross-sectional properties. This is a beam and bending, so I need the I, not the J. The J is for torsion. And that's, in this case, BH cubed over 12, since it's a rectangle, so I get that number. C is the distance from the neutral axis to the outside surface, which is just half of the thickness in this case. So that's a half an inch with my assumed 1 inch. And now I find the nominal bending stresses at the root of the cantilever in the notch. MC over I in both cases. The only difference is this is A's for subscripts and this is M's for subscripts. And the numbers are different. So I get 7,500 and 9,000 psi respectively for those two values. And now we have to deal with the stress concentration business. And for that I need to go to one of Peterson's tables, many of which are in the back of your book. And for those I typically need a couple of ratios. The difference in the dimension from the fat part to the skinny part, that's the D over D. And the ratio of the radius to the skinny part, R over D. Calculate those ratios. And this happens to be the one Peterson chart I pulled into the chapter 4 as an example, figure 436. It's also in Appendix C. Appendix E in the previous edition, Appendix C in this one. And in that chart, I find I don't happen to have an entry for 1.125 for the D over D, so I interpolate between the two neighboring values in the chart, and I get a 1.02, or 12 rather, for the A, which is the coefficient, and I interpolate to get this 0.221, put it in my fitted curve, and out pops 1.18. Not too bad. A nice big radius, so I've got a fairly low stress concentration. Now that's the case sub T, the so-called geometric stress concentration factor, which is what we would use for a static case. Just stop right there. But this is a fatigue case, and I want every little bit I can get. That case of T is going to give me a smaller safety factor than this case of F will, because I'm going to downrate this now because the material I picked is not all that sensitive to notches. So I can afford to reduce this a little bit. And that's where the Q comes in. So I go to the tables so-called Nuber factors right here, table 6.6. And these page numbers are third edition numbers, so it's going to be a little bit higher in your fourth edition. Probably 4 or 5 pages later. So I go into his table for a material with an SUT of 80,000 psi, which is this particular material, and he tells me the square root of A is 0.08, and I use that and the R of the notch, the radius of the notch, to calculate a Q factor of roughly 90%. So I'm going to get a 10% down rating of that 1.18. Not a hell of a lot, but I'll take whatever I can get. And it brings me down to 1.16. I probably could have ignored it, and I wouldn't have been much different. But get as accurate as we can. So now I'm ready to use this K sub f and its cousin K sub fm, which I haven't yet figured out, to bump up the nominal stresses to represent what they are locally in the notch. Now, don't get the idea that these are fictitious increases in stress. There really is higher stress in the notch. And if you did a finite element analysis of that part under that loading, you would see, it would tell you there's more stress in the notch. It's really there. And we're just making an estimate of that. These factors would come up with long before finite element was thought of. Finite element's been around about 40 years, if that, maybe 30. I remember the first time I used finite element. It was probably in the 60s. Was that Polaroid? That would have been early 70s, maybe 1970-ish. So that's 40 years. Time flies when you're having fun. So 40 years ago, it was just starting to be used. Not very much, but now it's very, very heavily used. So anyway, that's off the point. So I bumped these up, and these are now called the local stresses as opposed to the nominal stresses, the stress in the notch. And where did I get the KFM? Well, I skipped over it. Here's right here. I didn't even notice it. Here's the KFM right here. There's the KF. So down to there, down to K is the KF, the 116. My eye jumped down to here, and I thought I had done it. So here we have to ask ourselves if this KF times the maximum stress that I happen to have, that's going to be using the 5500, was it, moment, is less than SY, then I'm going to use the whole value of KF. So I do that calculation. Take the KF, which I just figured out at 116, take the maximum moment, which was 5,500 inch-pounds, multiply by the C, divide by the I get 19,000 and change. My SY for this material is 60,000. So I'm never going to yield in the notch. I think that's a good thing. I really don't want to yield the notch. I'd much rather be below the yield point in the notch, because then I'm not going to start growing cracks. So I'm happy with that, but it says I better put the whole K sub f on the mean stress. Oh, big deal. It's only 116. So we multiply the 116 by that again, and we get that. So now I've got what purport to be good estimates of the stresses in the notch, both mean and alternating. So now everything gets doubled. Now I've got to do a von Mises calculation for both of them, for alternating and mean separately, and that's going to finally let me take those into that Goodman diagram and see where I sit for safety. Now, I'm violating my own tenets here a little bit. I'm not bothering to calculate the principal stresses in this example. There are equations, and I give them to us, I think it's 622, so I don't reveal them until we get into Chapter 6. But I can calculate the von Mises stress in terms of the applied stresses. That's sigma xa, sigma ya, sigma xa, sigma ya, 3 tau xya, because we don't have any sigma y in this particular case, so those terms are 0. So we just have the sigma x squared sub a and the 3 tau xy squared sub a. I don't even have that in this case, so there's no torsion. So I really just have this guy, because this is 0 also. In which case, it's going to turn out to be equal to the von Mises and be equal to my applied stress. I have a uniaxial stress case here, much like the tensile tester, right? And in those cases, the von Mises is equal to the normal stress. So I could have, knowing that, I could have not even bothered to do the calculation, but I think it's just easier to set it up and do it all the time. You don't have to worry about whether you forgot whether it's there or not. So I'm going to end up with the same von Mises numbers as I had up here in this particular case because I just have a unidirectional stress. Now I got to look at my material. And I got to get the endurance limit. So we go through the usual rigmarole. Take half of the SUT. That's 40 grand. I don't have a round part, so I got to use a trick to sort of relate this rectangular thing to a round part. And the trick says, take the area that's subjected to 95% to 100% of the stress in the cross section, which is just the outer rim of the top and bottom. We only care about the tension side anyway, which would be the top in this case. And so I take, where did I do it? There it is. So 0.05 is 5%. D is the height, right? That was the 1 inch, and B is the width. So I'm taking 5% of the height times the width. That's a little strip of area across the top, and I'm finding out that's worth 1/10 of a square inch. And then I put it into that formula, which is simply converting it to a donut that has that same area. So it's an analogous round thing that I can compare to my test specimen, which is 3/10 of an inch. So I can then use that to determine a size factor, C size, which it looks like turns out to be 0.859 here. I give you the equation references. I didn't write them out here. So C load is equation 67A, and that, you may recall, has only two values. It says for bending, use 1, and for axial, use 0.7, I think it is. And this is bending, so it's 1. And then the C size factor, as we just discussed, that's coming out of this. There's the equation that I get to approximate at 0.859. C surface, machined finish, equation 67E tells me that 0.85 is a good estimate for that. C temp, this thing is at room temperature. Reliability, 0.753. Did I say what percent that is? Yeah, 99.9%. I don't recommend using 50%, which would be 1. You know, whether you use 99.9, 99.99, or 999, yeah, that's your choice. I think you ought to be up somewhere up there because you saw a scatter that was below the Goodman line, right, in those plots. Some material specimens are not going to deliver the stated value, the advertised value. So this essentially derates it and says I'm going to draw another line down below that, which is where 99% of them stay outside, right? Not 50%. And I get a usable strength endurance limit of 22,000, call it. And I started with 80. That's roughly a quarter, right? That's typical. So now I have to figure out my safety factors. I'm using the case 3 here, which assumes the alternating and mean components will have a constant ratio. I didn't, in the interest of space, I didn't show all the others in the example, but in my spreadsheet, in my TK solver file, I know I calculated all 4 of them. So this is the equation for the intersection of two lines. SE, SUT, of course, are the two intercepts of the Goodman line, right? Starts at S sub E on the alternating axis, it goes down to SUT. So that represents that line. It also shows up in the denominator. And sigma prime A, that's the point where I am on the diagram, right? That's my alternating stress. So that's how high up I am on the critical axis. And sigma m prime is how far to the right I am on that mean stress axis, and it turns out to be 1.9. And that's good. It's close to 2. I think that'll be acceptable. I'll give you a couple of tables full of data that are right out of the TK file, so you can see all the intermediate numbers. And I say, well, 1.9 is okay, but I could probably do better. So I go in there and I calculate the deflection at 12 thousandths of an inch, which I guess was within the spec. And I say, well, let's kick it up to, where do I say the number? Oh, this is what I had with the fully reversed. That's where this is coming from. I had 2.5 and 5 thousandths. So, and I'm at the same size as the fully reversed, right? And the loads are the same magnitudes. I've just brought in a mean load. I think the top to bottom is the same as before, but I've brought in a mean load. So that points out the fact that the mean stress is hurting me. I'm getting a lower safety factor with the same cross section by reason of having introduced the mean stress. Okay. So if I want to get back to the 2.5, it's easy enough to do. Just add a little meat to the pie here, and I crank up my little d was 1 inch. I make it 1.2 inches. Crank big D up to 1.4. I can buy a 1.5 inch piece of stock right off the shelf. I can machine that down to, a 1/10 of an inch off, clean both sides up to get a good clamp surface, machine the rest of it down to the 1.2, and I'm done. So this shows you all 4 safety factors for this particular case. So there's my stress state, sigma A prime of whatever, and sigma mean prime of whatever. There's my S sub E, which is 22,000, coming down to 80,000 over here. There's my 60,000 worth of yield going up at 45 degrees. And if I had what I call case 1, I've got a safety factor of 8.6. If I had what I call case 2, I got 3.1. Case 3, I got 2.6. And the shortest way out of the envelope is 2.3. So they're all over 2, and I say that's fine. I'm happy with that. I'm not going to read this list to you. This is right out of the book. But I give you a set of steps. They're pretty commonsensical. You actually could start almost anywhere in this list. I've got to get the material strength. So I've got that as the first step. I'm going to get my modified Goodman diagram for the material I picked. Then I'm going to calculate the 2 sets of stresses, the mean and the alternating, and convert to von Mises. After I put the stress concentration on first and then do the von Mises. Just do the von Mises once. So jack them up by the stress concentrations as appropriate. Then convert them to von Mises. And then plot your alternating and mean on that Goodman diagram and figure out the safety factor, or all 4. And you're done. This is the general case. And because it's general and incorporates all the others, you can use this all the time for anything. In other words, fully reversed is satisfied by the Goodman line. It just happens to be over on the alternating axis, right? I don't have to draw the line because I never go off in the mean direction. So I could actually use the same spreadsheet for every case I ever run into and just set the mean stress to 0. And I got it fully reversed. And if I have the so-called repeated case, which is fairly common, which means it goes from 0 to something back to 0, like this all day long, then the mean is equal to the alternating. Well, that's just different numbers in the same spreadsheet. So I have done that, just what I said. And on your disk, there are examples. Every example in the book is there as TK Solver, MathCAD, MATLAB, and Excel. And in this last slide, I think I'm suggesting example 6.6 is a little more complicated because it's got multiple stresses. And it's the same problem you've already done for homework. And I give you some suggested numbers here and a material of aluminum. And what I'm suggesting you do is go onto your disk with the book and get the example for this 6.6 and go in and monkey the numbers around to match this and see what you get. So that'll help you see how to put a program like that together, and you can modify it to do a different problem and so forth and so on. That's kind of an exercise, not a really homework problem, nothing to pass in.